In the previous video, we implemented the send method on the response, and it takes a parameter which is of type TCP stream. But this implementation would be better if we can make this function more generic by changing the parameter type from a concrete TCP stream to anything that implements the write trait. This will make the code more generic and flexible. For example, for unit tests, we won't have to pass a TCP stream here. We would be able to pass a vector and it will still work. There are a couple of ways to pass traits as parameter, and it is a bit more complicated than passing concrete types around. So let's try to swap the TCP stream with just write. This will compile, but the compiler will give us a warning. It is telling us that trait objects without an explicit DYN or DIN are deprecated. So this syntax of writing a trait directly as a type parameter is being deprecated, and it is telling us to write DYN before the trait. Okay, it's pretty easy to just write DYN before the trait and call it a day, but what is actually going on here? DYN stands for dynamic, and dynamic comes from dynamic dispatch. Let's think about the problem that we have here. At compile time, the compiler knows that this function receives a parameter that has the write function, because this parameter will implement the write trait. And that's great. We can call the write function in the body of our method on this variable. But the compiler doesn't know exactly which write function to call. Because remember, in the trait, there is only the signature for the write function. But the actual implementation for the write function will be in the TCP stream, or in the file, or in the vector. All of the implementers have different implementations of the write function. And we can pass any one of these types as a parameter to this function, and the compiler has to figure out exactly which implementation of the write function to call. It is called dynamic dispatch because the concrete function implementation to be called will be resolved at runtime. And this is achieved by creating a mapping between the concrete implementations of the trait and the trait itself. This mapping is called a vtable, and it is just a table with function pointers. Think about it this way. When we call a normal function on a concrete type, this code will be compiled down to a simple call assembly instruction that jumps to the address of the function that we are calling. But in this case, we don't know the address of the function that we're calling at compile time, so we can't just output one assembly instruction. When we are calling functions on the stream now, when it is typed as a trait, at runtime the code will have to jump to the vtable, find the correct function pointer to the implementation that we want, and then jump to that function. So there is a clear runtime overhead if we are using vtables. It doesn't sound like a lot, but it can get costly in the hot path of your application. But Rust also provides us with another approach to solve this problem. It is called static dispatch. As the name suggests, instead of being dynamic, which means that it's resolved at runtime, it's static, which means that it's resolved at compile time. And to use static dispatch, all we have to do is change this DYN with impo. Now we are saying that this function accepts any parameter that implements the write trait, and the compiler will make sure to resolve all the concrete implementations that we would use. To do that, at compile time, the compiler will look at every single place where this function is called. And more specifically, it will look at every parameter that can be passed to this function. So throughout our entire code base, every call to this function, the compiler will look at the type that we are calling this function with. And for every different concrete type that we are calling the function with, it will just copy this function and type it with the type it's being called. So let's imagine that we have this function with this definition, and at compile time, the compiler sees that we're calling it with a TCP stream here. What it will actually do is it will generate a new function. Let's imagine that it will call it send, but with TCP stream. And this part here will be the concrete type that we were using. If also somewhere else in the code we are calling this function with a file, the compiler will generate this function again, but this time it will be working with a file. So we end up with a lot of implementations of the same function, each one expecting a different argument. And by doing this, there is no need for vtables, there is no more runtime cost, because every time we call this function from somewhere, it will be called with the concrete type, so it will be faster. Generally, this is the preferred approach between the two. The main downside of this is that the compilation will be a bit slower because the compiler has to generate more functions, and we end up with a larger binary because one function will be implemented multiple times. This can be an issue on some embedded systems, but for the average use case of our code that will run on some server that has 60 gigabytes of RAM, this is not a problem. But what is great here is that Rust provides both of these approaches and lets us, the developer, decide which one we want to use.